Okay, guys, the last Gauss's law video is a sphere with uniform charge density. So this would not be a conductor. Conductor is going to have charges in an electrostatic situation. The charges are going to accumulate just on the outside of the sphere. So we have something that is some insulating material where maybe you've got this insulating material where the negative charges have been stripped off uniformly so that the charge density is uniform, meaning any little volume chunk that you take out of this sphere, you're going to have the same charge to volume ratio. Okay, so we have some uniform charge density rho that is the total charge divided by the total volume. That ratio would be the same for any little volume chunk that you take out of the sphere. So if you just, if you hack off a chunk of material here and you do, the charge in that region divided by the volume in that region, you're going to get rho. Okay, so it's a uniform charge density, a lot like we did before with finding moment of inertia and things like that with mass density, and also with charge density to find electric fields. We've done that before. Okay, so we've got a uniform charge density here. So the electrons have been stripped away uniformly, leaving behind an overall net charge of Q. And we're just going to call that guy Q total. And this sphere has a volume of V total, which of course, because it's a sphere, would be 4/3 pi r cubed. And here I'm going to use capital R because that is the size of my sphere. Okay, that's not going to change as I change my Gaussian shape. That's what the Gaussian shape, I'm using little r because it's arbitrary where I draw that shape. But for my actual sphere, the physical sphere itself, I'm using capital R because that's a constant. So 4/3 pi r cubed, and then Q is the total charge on the sphere. Okay, so what I'm going to do is I'm going to go from outside in. Let me start with the simple portion of the Gaussian, or the simple Gaussian shape, and that's if I were to draw a Gaussian sphere completely around everything. Okay, completely enclose this sphere. So this would be when R is greater than big R, when my Gaussian shape is bigger than the sphere itself. Okay, when I do Gauss's law, the surface integral of E dot A is equal to the total charge enclosed divided by epsilon naught. And again, that's the electric flux for this orientation. The electric flux, Q enclosed over epsilon naught. Well, when I'm beyond the actual sphere itself, then I am going to capture all of the charge, total. So that Q enclosed is just going to be Q total. And this looks pretty simple. This dot product is satisfied everywhere on the sphere. So this just becomes E times 4 pi r squared. Again, I'm using little r because where I drew or how big I drew that Gaussian sphere is arbitrary. I could have drawn it as large as I wanted as long as it was bigger than capital R. So 4 pi little r squared is equal to Q enclosed, which is just all of the charge divided by epsilon naught. And this is going to simplify really nicely. When I divide over 4 pi r squared, I get Q total over 4 pi r squared epsilon naught. But again, 4 pi epsilon naught, 1 over 4 pi epsilon naught we know is just K. So this becomes KQ total over r squared. This is identical to a conducting sphere or even a point charge of charge Q, KQ over r squared. So once you're beyond the shape and what's going on inside of the sphere, this thing just looks like a point charge or it looks like a conducting sphere, KQ over r squared. So pretty simple. Where it gets interesting is inside of the sphere itself. So if I've got a smaller Gaussian shape. So now I want to look at what happens when I am inside of R. So when R is less than big R. Okay. When I'm inside of the shape, you'll notice that I'm not encompassing all of the charge. I'm only getting a portion of the charge. So I have to figure out a way of writing this much charge in terms of the total charge on the entire sphere. And I'm going to do that with rho, okay? If rho is charge per volume, then the charge of any little chunk that I look at should be equal to rho times the volume that I'm looking at, okay? So what I'm going to do is set up Gauss's law. The surface integral of E dot A is equal to the total charge enclosed divided by epsilon naught, okay? Again, the electric field and the area vector are going to be parallel everywhere along the surface of my Gaussian sphere because we've got spherical symmetry. So this left side, again, is just E times 4 pi r squared. But again, r must be less than big R for this condition. Okay. Charge enclosed. Well, how much of the charge am I getting inside of that sphere? Well, I'm only enclosing a portion of the sphere. So if I take the charge density times the volume of my Gaussian, not the entire volume, rho times the entire volume, rho times the entire volume should give me all of the charge, total. But rho times my Gaussian volume should give me just the amount of charge that's inside of the Gaussian shape. So charge that's in the Gaussian shape is going to be rho times V Gaussian. So I've only got inside of my Gaussian shape, I've got rho times V of the Gaussian sphere, all divided by epsilon naught. But the Gaussian sphere has a radius of little r, so I know how to write volume of a sphere. That's just 4/3 pi r cubed, okay, over epsilon naught. I'm going to go ahead and divide over the 4 pi r squared, and E, the electric field inside of the insulating sphere with uniform charge density, is rho times, well, when I divide a 4 and a pi, this 4 and this pi are going to be gone. R squared is coming over. Take away from r cubed, that's going to leave me with just r to the first power. So I get rho times r divided by 3 epsilon naught. Okay? Again, rho is something that I kind of made up here. They said charge density. I wrote it as rho, so I need to go ahead and replace that guy. But I know that rho is the total charge of the sphere divided by the total volume of the sphere. So now what I'm getting is I'm getting that enclosed Gaussian shape written in terms of the total charge, which is something that I know or was given by College Board. So the electric field here, substituting in rho, I get rho is Q total over the total volume of the sphere. Well, that's 4/3 pi r cubed, again, times r and divided by 3 epsilon naught. Well, the 3 is going to cancel here. And you'll notice that I'm coming up with a 1/4 pi epsilon naught. 4 pi epsilon naught is just K. So electric field is K times the total charge divided by r squared, or sorry, r cubed, times little r. Okay? Well, this is very different than anything we've seen. It says that inside of the uniformly charged insulator, the electric field is not decreasing as a 1/r squared like we've seen before. It's actually increasing linearly. So you would say the electric field here, K, Q, and capital R. Well, these are all constants. Total charge and capital R, the radius of the sphere, that's dependent on the shape of the physical object itself. K is the Coulomb constant. So these are constants times R to the first power. So I would say that the electric field for this insulating material with uniform charge density as a function of radius, it's different before and after the radius of the sphere itself. So when you are inside of the sphere, we see that the electric field is linear. The electric field is linear inside of the sphere. The moment that you reach the radius of the sphere, we know that it becomes KQ over R squared. Okay, KQ over R squared. The one thing that I want to check is, well, I know that the shape of the curve is 1 over r squared. After this portion, I know it's 1 over r squared. I just don't know where. Okay, so what I'm going to do to figure out where that 1 over r squared curve needs to go, or how high it needs to be placed, is I'm going to look at this guy as r approaches big R. As R approaches big R, you'll notice that if I plug in big R, capital R here for R, then I'm going to get at R equal R, the electric field is K Q total over R squared. So that means this guy is going to approach the electric field that I get beyond that region. So these are actually going to be connected. I'm going to start that electric field right here where I left off. This was the linear electric field inside of the insulator. And I'm going to, right where I left off here at R equals R, then I need to draw a 1 over R squared proportionality. So I'm just going to write here proportional to 1 over R squared. Here, it's proportional to R. It's linear, and then it's 1 over R squared. So it's a really interesting thing that happens when we've got that uniform charge density. Look for a linear electric field. And that's something you want to kind of, we don't have multiple choice questions this year, but if we did have multiple choice, it's something you would want to kind of memorize, and maybe it might be useful for you to memorize even for the 2 free response that you guys are going to see this year. The uniformly charged sphere has a uniform electric field, and then once you get outside of the sphere, it just looks like a point charge. It's KQ over R squared. Okay, so that's it for now.